Hi everyone, welcome back to our channel. I hope you and your family members are doing good because that is the most important thing, and for rest we are here to talk. So we were following our pattern wise DSA sheet. In this we were doing tree topic and the pattern was BFS. Today we will solve the last question from this pattern, and which is maximum width of a binary tree. So let's read the problem statement. It says we will be given the root of the binary tree and we have to return the maximum width. What is maximum width? It is a maximum width among all leaves. So we have to take care of the distance between the two leaves, leftmost and the rightmost, from a particular level. So the width of one level is defined as the length between the end nodes, the leftmost and the rightmost. That's what the definition is. Where the null nodes between the end nodes that would be present in a complete binary tree extending down, means if there are no null present between the leftmost and the rightmost. So here as you can see, from the leftmost to rightmost, one more node was supposed to be present here, but as it is not there, but still the width will be 4 and not 3. So basically it's not about the number of nodes in a level, but it is about how many nodes were supposed to be present. Even if it is null, we have to count that, and from the last node to the first node. So if we will talk about the indexing, the indexing for this will be 0, for this will be 1, for this will be 2, 3, 4. Here it is null, supposed to be 5, and here it is 6. Similarly, null supposed to be 7, 8, 9, 10 as null, 11 and 12. Okay. So the leftmost, what is the maximum width? For this level it will be leftmost and rightmost difference, which is 0 minus 0 plus 1, which is 1. Similarly for this, rightmost 2 minus leftmost 1 and plus 1, that will be nothing but 2, and that's what 2 width. Similarly for this, rightmost 6, leftmost 3 plus 1, which is nothing but 4, and the width of this level is 4 because 3 nodes present and 1 for the null value. Similarly, rightmost 12 minus leftmost present node, which is 8. Remember, not 7. See, we have to consider the null nodes if it comes between the leftmost and the rightmost. Okay, but this 7 which is null, it's outside it, so we will not consider or we will not count it. So 12 minus 8 plus 1, which is 5, correct? And it is 5 only, 1, 2, 3, 4 and 5. Correct? So this is what we are supposed to give. So for sure we understood from the definition itself कि we don't need to give the number of nodes present in that level. No. How can we get कि there was null? We have to count that also, because if you are thinking for storing the values and then count the number of nodes, it is false, because in this you just saw कि 5 number of width will be there, not 3, correct? Now if you are thinking ki store null also, okay, you will store the nulls, you will count it, but you will end up storing this null also, which is not required. So hence anyhow we have to play with the indexes only, means we have to assign the indexes to every nodes, and whatever node has the indexing we have to subtract, means rightmost minus leftmost plus 1. This is what we are supposed to do. So if we have to give the indexing, so for the very first node, suppose the indexing is I, then what will be the index for left child? It will be 2 into I plus 1, correct? If it is 0, then 2 into I plus 1, which is 1, and 2 into I plus 2 for right, it will be 2 into I plus 2, correct? So as if the I is 0, then this will be 1 and this will be 2, correct? Now for 1, 2 into I, which is 2 plus 1, 3, and 2 into I plus 2, which is 4, correct? Okay. So with these formula, we will assign the indexes to every nodes. Done? Either by BFS or DFS approach. Okay. Now the task is कि we have to calculate the width for every level. So in BFS, so it is very easy. How? Because we have already saw in the BFS level order traversal कि how Q stores all the nodes present in that level. So along with the nodes, if we will save the indexes also, so definitely for this much size, we will get the rightmost index from the right side element and leftmost element from the left side element, and the difference between that will be our width. It's very easy. What I said, कि if in the queue we will store node value and the index, correct? Okay. Now in the next, for the next level, node value and the index, node value and the index. Similarly for the next level, node value and the index, similarly 4, node value 3 and index 4, similarly node value 9, index 6. So what I said, ki this sublist stores all the elements present in 0th level. So this 0 will be my rightmost node minus 0 leftmost node plus 1. That will be width of that level. Okay. Now let's come on to the second one. Okay. Now second one says this will be the rightmost node, this will be the leftmost node and plus 1, which is 2. Correct only. Similarly for third one, rightmost node 6, leftmost node 3 plus 1, which is 4, which is the number of nodes. Now if you are thinking, then to for sure the maximum width will be present at the last level. It is not correct. Why? Because suppose this node was not there, then to maximum width will be only this, na? See, we have to consider the null, but only if it comes between the left and the right, which is actually the existing nodes. In the last level, the existing nodes are just 11 and 12, not here. So these nulls will not be encountered. So for the last level, the maximum width is nothing but 2, correct? 12 minus 11. So suppose if 4 was not there, so in the last level, what we will store? 7, 11 index and 6, 12 index. That's it for the last. So suppose 4 is not there. So 12 will be my rightmost node or index and 11 will be my leftmost and plus 1 will be 2. So 2 is the maximum width. So as you can see, it's not necessary that maximum width will be at the last level. So in this case, 4 is the maximum width which we got from the second last level. Okay, so that is why it is very important to play with the indexes and for every node to assign the indexes. So using the BFS means level order traversal, it is very easy, correct? And you know, QData structure only stores single element. If you want to store 2 elements at a particular index, means the node also and the index also, then we need to create the pair. Okay, and while inserting this together 1 and 0, we have to create a new pair assigning these values. Okay, so here we saw one thing. How many number of nodes are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. But the index was for 12. Can I say that? Even though number of nodes were n, which is 9, but the index went for 12. So if we see the constraint says that the number of nodes in the tree is in the range 1 to 3000. 1 to 3000. And the node value is from minus 100 to plus 100. Although we are not playing with the node values, means not doing the multiplication and summation, so we need not to worry for integer overflow. Okay, but considering the number of nodes, we are not sure how many indexes we have to apply. Means, as you saw here, only 9 number of nodes were there, but our index went for 12. Similarly, suppose if 3 was not there, this was not there, this was not there, we just have this. Means you can say only 6 nodes, but still the indexes will be till 12. So how the index varies? Is it as per the number of nodes? No, it is as per the levels. And for every nodes, we have 2 children. So the number of nodes also varies. In every level, it's 2 power n. Means for first level, if there were only 1 nodes, then next level it will be 2 power n, means 2 power 1, means 2 children. Correct? Similarly for the next one, 2 children were there, so 2 power 2, which is 4 children. So 1, 2, 3, 4. Similarly, next time it will be 8 nodes. Correct? Okay guys, my bad, it should not be like this. First though we will assign, suppose this is null, so 5. Correct? For this also null, null, and for this also null, null. Remember? 2 nodes. So 7, 8, 9, 10, 11, 12, 13 and 14 will be the index for it. Correct? So we have to store 14 as the index and we have to store 13 as the index. And if 4 is there, so the last, and this is the rightmost. So rightmost index is 14, leftmost index is 8 plus 1. So if we'll subtract, this is nothing but 7. So 7 will be the width in this case. Okay. So if you saw, it's nothing but 2 power n minus 1 indexes. Okay. 1, 2, 3, 4. 4 levels. So here total 15 nodes could have been adjusted, correct? Because we have proper places for it. So hence for 4 levels, it's 2 power 4 minus 1, means 16 minus 1, 15. So guys, when it says the number of nodes can be 3000, for the worst case scenario, you can consider ki suppose a tree looks like this. Instead of this, we have tree something like this. Okay? Only last nodes it has. Okay, so how many number of nodes are there? 1, 2, 3, 4, 5, 6, 7, correct? But what is the index we have to assign, which is 0 for this 1, 2, for this 3, for this 3 to the 6 plus 1, 7. Similarly, 2 to the 4 plus 2, 6, and for this 14, correct? So as you can see, just by having 7 nodes, we have to assign the index up to 14. Similarly, if we'll add one more, then it can go about 30, correct? 14 to the 28 plus, and this will be around 15, correct? So by just having 9 nodes, index went to 30. Similarly, we'll add one more. Just by having 11 nodes, the index will be from 16 to where? Can I say 62? Yes. Then by next, just adding one nodes, just by having 13 nodes, the index will went for 114, correct? This is how it varies. So this was having 4 height, correct? So I can say the index went for 2 power 4 minus 1, which is 16. 16 minus 1, 15. From 0 to 14 means 15, and it says it will be less than equal to 3000. Can I say? So here instead of 4, if we say h, this is what nothing but number of nodes can be present at a particular height, and it says it can be 3000. So let's find what is that maximum height where the number of nodes can go till 3000. So if you will calculate, the h will come near around 11. Means for 2 power 11, 3000 number of nodes can be adjusted. 3000 nodes means 3000 indexes also we have to assign. So 2 power 11 integer can hold it, so it's totally safe. But if it goes beyond means 2 power 32, then storing it in integer index is not possible, and hence we have to convert into long. And one more key observation is कि anyhow we have to, like when we have to find the maximum width, we are doing the rightmost index minus leftmost index plus 1, correct? But when it is about 0, it's about from 1 to 2, it's about from 3 to 6. Is there any other way कि instead of starting from 3, instead of starting from 1, we can start from 0, 0? Yes, it is. And what's that? Instead of adding like formula like this, 2i plus 1 and plus 2, let's do 2i, and for this 2i plus 1. Now what will happen? This is 0. So next time 2 into I 0 and 2 into I plus 1 1. So this is how it will overwritten 0 to 1. Now similarly this is 0. So again it will be 0, and this will be 2i plus 1, which is 3. So this will be 0 and this will be 3. And see, still the maximum width is same, 3 minus 0 plus 1, 4 only. Now similarly 0 into 2 means 0, and this is 3 into 2, 6 plus 1, which is 7. So earlier also the difference was 8, and here also the difference is 8, correct? So what we actually achieved, instead of storing the last index as 2x, now we are able to fit this with x. So for the deepest level of trees, instead of storing 2x, storing x will help us to get the indexes, and this can lead to overflow. But still on the safer side, instead of storing the indexes in the integer format, we will go with the long format. So what we will do, let's see what we will do. First, as said, कि in our queue data structure, we will store the very first root node, let's say 1, 2, 3, 4, 5, 6 and 7. So let's say 1 we will store, and the index for it will be 0, correct? Now until our queue is empty, we will keep on continuing this same process. So first we will get the size. Ki size of the queue is queue dot size. So initially what is the size? Which is 1 only. Okay. And now for this many size, we have to run the for loop ki for int I is equal to 0, I less than size, and I plus plus. Now what is our task? Our task is to pop the node and store their left and right children with their indexes. As we have popped, first we have to pop, right? So first we'll pop, and let's store, as it is a pair type, so current queue dot poll. Why it is a pair type? Because in our queue we have not stored the root value, but we have stored in the pair format. Okay. So now our task is to check ki if our current dot root has the left child. Okay. Then store left child in queue with index 2 into I. Now what is I? Instead of I, we have to say, because we have got current, so 2 into current dot I or index, whatever we have stored. Now similarly, if our current root has right child, then store right child in the queue with the index 2 into current dot I plus 1, and that's it. Now after coming outside this for loop, can I say ki in my queue I have all the elements present from that level, correct? Now what is our task? Suppose in this case, if we would have inserted this and this, then what is our task? To get the index of this and to get the index of this. Can I say that? But after one traversal of for loop, in our queue this level nodes has been popped out, and in our queue we have this. But we have to check the width of the first. So how we could have done? Very easy. When we started popping the element from that level, it is very important to store the first index and the last index. So where is our first index? First index we can store before popping from queue by queue dot peak. This is our first index. Now last index also we will initialize, let's say with the first index itself. So here the first index is 0. Now we'll pop, and last index also will get 0 only. So after popping, as we have popped, so we have to keep updating our last index with what? Can I say current dot I, which is nothing but index. Now what will happen? This node will get popped out, correct? And the children's next and next, 2 and 3. So 2 children with 0 index and 3 children with 1 index will get inserted. Now next time, before popping this, first we will come here, we'll check is the queue empty? No, it is not empty. So we'll calculate the size. First index from queue dot peak, we will peak. But first when we will peak from queue, we have a pair. We have to read this, which is 0, and this is nothing but queue dot peak dot I or index, however you have stored, correct, with a variable. So now first index will be 0. Now we'll start, like last index also will initialize from 0, and we will pop or we'll run this for loop for 2 times. First we'll pop the current 2, correct, and we'll get, and in the last index current, which is 0 only, will get initialized. Now our task is to store this children of 2, means 4 children with what index? See, again, what was the index of 2? 0. Towards its left, what we sent? 2 into index only. So 2 into 0, 0 only. So for 4, what will be the index? Again 0. Correct? Now next time we'll pop 3. Okay. Here it will pop. Last index will get updated with current dot I, which is 1. So last will become 1. Now left child and right child, whatever we have, we will store. What will be the index? What is the index of 3? 1. So 5 is the left child or right child? Right child. So again we'll come here, 2 into 1 plus 1, which is 3. So for 5 child we will store 3 index, correct? Now we'll come out of this for loop. Now what we have? We have first as 0 and last as 1, but we have to update our maximum width. So after coming outside the for loop, our task is to update the max width, but with max dot max. Previous max width is the maximum width or this current one, and current one is nothing but last minus first plus 1, and that's it. And after coming outside, we can simply return this maximum width. Isn't it easy? So time and space complexity will be O of n only, because we are traversing and storing all the nodes in our queue data structure, correct? Now here is the code. First we will create the pair. Now check if root is null. We'll create the queue data structure, and inside it we will store root and its index. Now we'll check until it is empty, calculate the size and run the for loop for that many size. Now we have to initialize our first and last index for every level. First will be nothing but queue dot peak, very first element, and last we will keep on updating here in the for loop after popping every element. Now first we pop, with the index we'll read the last index, and we will store left and right child in the queue if they are present. After coming outside this for loop, which was supposed to run for every level, and now we can calculate the maximum width with the difference last minus first plus 1. But we have to convert this in integer format, because the question says it is guaranteed that the answer will range in the 32-bit integer, signed integer. It means it will be in the integer range. And at the end, we will return our maximum width. So the time and space complexity for this code will be O of n. So this is done. Now let's try to submit this. So I hope you understood why we played with that indexing. Okay. This was the code in Java. Here is the code in C++ for the similar logic, and here is the code in Python with the similar logic, but with the BFS approach. Now how can we do with the DFS approach? It's very simple. Let's discuss. Here in the BFS approach, we knew कि last and first index is already there in the Q data structure. So we don't need to maintain the levels also. But in depth wise, when we start from the root node and we go towards their children, suppose we are at 4. So to calculate the maximum width, 5 should also have been encountered. But as it is depth wise node, so we don't have encountered 5, 7 or 3 yet. Correct? So it is very important to store all these first indexes in the levels. So what we will do now, like we will create a, let's say, first index array where we will store the first indexes of every level. So here first we will check ki what is the size of the current index. Okay, what is the size of the current array? We will say it's 0, correct? And the level is also 0. So size is equal to level. We already did when we did the DFS level order traversal. So we will insert 1, correct? Now what will happen? Listen it very carefully. We'll go on the next level, which is level 1. Size is 1. So we have not visited the size yet. So 2 also we will insert. But instead of inserting the node values, we will insert the indexes. Remember. So what we'll do, we will insert the index. Now again we are going towards this. So 0 was the index. For left child, 2 into I, which is 0 only. So for this also 0 only. Okay. So again we will insert 0. Similarly, we'll go towards 4. Again we'll insert 0. Why? Because 0 is the index for this left side, 2 into I, which is again 0. Now again 0. 0 for the 4 also and 6 also. Now listen it very carefully what will happen. We'll go back. Now we'll come here. Once we encountered the rightmost nodes, then only we can say ki yes, now we can calculate the maximum width, because for the leftmost index we have stored here and rightmost index we are currently present, correct? So now we'll go from here to here. So 2 into I plus 1, correct? So 1 is the index for this. So we'll check, hey, ki current level is 1. What is the size of this first index? It will say 4. Means okay, we have already encountered 4 indexes. So for level 1, first index is already there. So what we will do? We will read the first index from here, okay, and we'll simply do this last one minus index plus 1, which is 2. Similarly, we'll go towards this side. Again, we'll check current level is 3. Maximum size is already 4. Means for level 3, the first index has already been stored. Correct? So this. Now if you are thinking ki why to store, it is so 0 only for every nodes. It's very necessary. Why? Because suppose for this we don't have 6. Suppose. Okay. And for 5 we have this will be 6. Correct? Listen it very carefully. So now in this case what will happen? For 4 node there will not be any nodes. We'll go back, we'll come here, and now when we'll go towards left side, what will be the index for this? 6. So we have to store 6 for the 4th level. Now when we'll come on 7, the index is also 7, so we'll get what is the first index? 6. So 7 minus 6 plus 1, which is 2. So the maximum width for the 4th level is 6 and not with 0. So hence it is very important to store the first nodes in the array, and when we will encounter the last nodes, with the help of first nodes array, we'll get the index and we'll do the difference and store it. Very easy. It's just about storing the first indexes in the array with the DFS approach. So let's discuss the code. First we'll make the array. As we are storing the indexes in the long format, so the type will also be long. Maximum width we have to initialize with 0, and in the main function we'll call the DFS and return the maximum width. Now what we are doing in the DFS function? First the base case check, if root null, return then and there. Now what we are doing, this code is to insert the index, first index in the array only when level is equal to array dot size, because that guarantees ki as of now no such index has been encountered. Okay. Now after this we have to store the maximum width. How we will store the maximum width? We'll compare whatever is maximum and the current one. Index is nothing but suppose we are at 5. Okay. So what is the current index? 3. Now we have to subtract with what? What is the level of 5? 0, 1, 2. So we'll go in the first index array. From the 2 we will get the index which is 0. So 3 minus 0 and plus 1. So we'll get 4 as the maximum width. So that's why we are doing index minus array dot get first index with that level plus 1. And after this our task is to go towards the left child and right child. Okay. So remember, we'll go towards left side with 2 into index and right side with 2 into index plus 1. Why we are doing this? So that at every level we will have indexes from 0 to n minus 1, 0 to n minus 1. Okay. So now let's run the code. Here also the time and space complexity will be O of n, O of n. Okay, so let's try to submit this code. Why the space complexity will be O of n? Basically, space complexity will be the height of the tree. If it is skewed tree, then the space will be O of n. If it is balanced binary tree, then the space will be logarithmic of n. I hope you all know if you are following my playlist. So this was your Java code in DFS. Here is your C++ code with the similar approach, and here is your Python code with the similar approach. So if you understood this maximum width of a binary tree with the indexes, why we applied that, how it will get overflow, and what is the DFS and BFS code, definitely you are allowed to go in the sheet and mark the last question from the BFS pattern as done. So I hope you are liking the video. If yes, make sure to like the video and subscribe the channel if not yet subscribed. Because we are following the pattern wise DSA, and also in tree we are trying to do the code both in BFS and DFS approach and understand the difference when to apply what approach. So in this case, it's always better to go with the breadth first search approach, because you don't need to save your first indexes also, and you don't need to maintain the level in the DFS. Although we can do the coding via both approaches because both are linear only. So that's it. I'll attach the sheet link and my social media link in the description. Let's meet in another video with some more interesting questions, topics and patterns. Till then, keep learning, take care of yourself and your family too.